So here we have the new test stand equipment rack that we'll be using for the next static engine test. So it's separated into a few sections here. Up at the top we have our sensor inputs. So each one of these connectors, well, they're not fully populated. Each one of these 32 connectors goes to a single-ended 12-bit analog input that we'll use for measuring things like pressures, temperatures, flow rates, things like that. Below that we have our outputs here. These each go to a different valve on the test stand, so that might be like a high-pressure helium solenoid or the propane igniter valve or something like that. And so we have a bunch of different voltage outputs here, 12 volt, 24 volt, 120 volt AC, for the different types of solenoids we have. Here we have our networking equipment. We have a network switch as well as just some inputs and outputs here. We have the 6 connectors here for the network cameras we're using for video for the test that have power over Ethernet. So we can power these cameras with a single cable as well as get data. We also have a few auxiliary connections here. Like the first one here, for example, goes to our remote e-stop so that we can emergency stop the test and reset all the valves to a safe state from a distance. Here we have our data acquisition computer. This computer does the valve sequencing as well as capturing all of the analog data from all of our sensors. And this gets saved to a database so we can look at the data after the test as well as view it live from our control station. The final computer down here does the video for the test, so it'll receive all the streams from the network cameras connected here as well as a DSLR connected to an HDMI capture card. It'll also re-encode that stream so we can see all that video easily from the control station, where we can watch those streams, make sure the combustion looks correct, everything like that. And then down at the bottom here, we just have a few power supplies. It's kind of unfinished down here, but we have 24 volt, 12 volt power supplies, and 5 volts for the data acquisition electronics. So here we're looking at the right-hand side of the equipment rack. At the top here we have the electronics for the data acquisition, all of the analog electronics. So that has the signal filtering for each one of the analog channels, as well as an individual adjustable power supply for each one of those sensors. And that connects to the data acquisition computer here, to the AddLink data acquisition card rig. Next here we have the relays that control the solenoid outputs. Each one of those also connects to an AddLink digital output card through a opto-isolation and a buffer, which gives us a safe way to control our solenoid outputs, especially the 120 volt solenoid outputs where we don't want any possible short or anything to damage all of our control electronics. And then of course we have the data acquisition computer and the video computer down here. Okay, so here we have our remote emergency stop button. And so I'll plug this into that auxiliary port I mentioned earlier. And so this allows us sort of a hard shutoff. When we press this button, it turns off, you can see the red light here, that when we press the button, it turns off the power to the relays here, which in turn turns off the solenoid outputs, which allows us a real safe and fast way and reliable way to turn off the valves in case anything goes wrong. We also have a software shutoff that runs a normal shutdown sequence, but this allows us, in case all else fails, we can at least turn the flow of our fuel off. So here we have the electronics we use to control the solenoids. The data starts at the data acquisition computer, where we have the AddLink digital output card. That connects to the DB37 breakout here. And this breakout has one wire. Each one of those goes to the relays here. In between the relays and the breakout, however, we have some opto-isolation to keep the rest of the data acquisition electronics protected in case of some sort of short, overcurrent, overvoltage, anything like that. As well as a buffer to drive the relays and some digital logic that is controlled by the e-stop button. This allows us a hard shutoff to turn these relays off immediately without having to go through the software of the data acquisition computer. So here we have some status lights. The green light shows that these boards are powered from the isolated 5 volt power supply. The red light shows that the e-stop is currently disabled, so the relays are hot. they're ready to be triggered. And the yellow lights here, each light when their corresponding relay is active. So here I'm just going to use a jumper to short out the input signal, just to demonstrate what the relays look like. So here I've turned the first relay on, and you can see the light come on, and you can hear the audible click. And that's as the contact switches, you can hear the contact switching. So these are the signal conditioning modules for the analog inputs. Each one of these modules here connects to one of the connectors on the front panel, where you would connect to one of the sensors, the temperature, pressure, whatever type of sensor it might be. And at the other end here we have the DB37 connector that goes to the analog input card in the data acquisition computer. So each one of these modules has the connector for the input wires from the sensor, as well as an adjustable power supply adjusted by the trim pod here. This allows us to get an individually controlled power supply for each one of the sensors, especially because a lot of the sensors run at different voltages, maybe 5 volts, 3 volts, 10 volts, 12 volts, anything like that. And this allows for a clean, isolated supply from each other. There's also some analog filtering here as well to help get rid of any high-frequency noise that might show up in the test equipment, maybe from a gasoline generator we might be using to power the whole system or something like that. So right now we only have 10 of the input modules populated. There's room for more of them to get to the full 32 single-ended sensor inputs. This allows us for some modularity in the design, where we can include different types of input modules if we wanted to have, let's say, a different supply voltage range or some different type of signal filtering. We can also span the input across these two modules here to allow for a differential input. We have to reconfigure some software, but in the case where we need a differential input sensor, we have that capability with the